All right, for this exercise, we're going to be doing it based on the lectures and the readings that we've had for animal movement. So this is going to be I'm going to start fresh with a new code, new script here. We're not going to build on any of the other ones that we've been working on, but right away that we're going to require a few libraries or packages, fields, require maps, geosphere, and require circ stats. And remember, if you don't have any of these, you can go ahead and come up here up into tools and install the packages yourself. Remember, you can just put in here whichever one you need. Remember, it's geosphere, and go ahead and click on it and it'll install. So all right, we're also going to load in our chlorophyll path again, our chlorophyll data. So load to reflect location of the sat data.rdata file. So let's go ahead and load. Desktop. Set data.rdata. All right, go ahead and load that in. All right, and we've worked with this object before. Remember, it's an array of chlorophyll and SST with lat and long with it. And what we're going to do right away, if we go ahead and image, if we image the array, let's do long, lat, all right, that's our chlorophyll array. It goes from 0 to 70. But one thing that we want to do is that we want to trim this down. So we're going to take just part of the equatorial Pacific in here. And so remember the dimensions of that are 1080 by 540 by 11. I'm just going to trim a bit out of it here. So we're going to say our chlorophyll matrix is going to be the chlorophyll array. Actually, we'll just go ahead. First thing we'll do is a chlorophyll array. We'll just take the first year. The first layer. So the dimensions of chlorophyll mat now are 1080 by 540. All right, and now we're going to take that chlorophyll matrix and we're just going to subset it. And the area we want to subset by is 3 to 250 and 170 to 320. Okay, so let's go ahead and look at that. Okay. .ch. Okay, so There's a bunch of chlorophyll there out in the middle of the ocean. What might be helpful here is if we subset our ln and lat. Our ln is going to be equal ln 3 to 250, which is the same as the x portion here. Lat equals lat, which is going to be 170 to 320. Right. So now let's do plot ln lat CHL lat. All right, so we are in, so here's the equator right here. So there's equatorial upwelling. We're going to trim out some of these values. We're going to be working with low chlorophyll values for this exercise. So let's do chlorophyll mat. Let's replace that where chlorophyll mat is greater than 0.3. We're just going to make that 0.3. So that's our ceiling. Let's now do the image.plot again. There we go. All right, so we've got a big expanse of ocean out here. Here's our equatorial upwelling, and we're going to go ahead and do some simulations. Should be fun. All right, so let's now create a threshold for behavior switches. So we talked about that a bit. Creating chlorophyll where the shark switches from a searching to a feeding behavior. So what we're going to do is we're going to design a shark that's going to have two different behaviors. One is searching and one is feeding. And that is going to be switched on and off dependent on the chlorophyll concentration. So the chlorophyll threshold for that switch will equal 0.15. And this is something that you can mess with. All right. Now, we also need to create what's called dispersion parameters that control how correlated each potential direction is in the feeding. So each one of these feeding and searching, so we're going to have, let's see, feeding and searching behavior are going to have dispersion parameters that are associated with them, and we'll get to what those are in just a second. So let's define our feeding dispersion equals 0.1, and I'll just make it disp. Searching dispersion will be 5. I'll just put a little note in here. Yeah. I'll just keep going here. Low values mean that sequential steps in the angle each animal swims are not correlated. So, in other words, animal is choosing random directions to swim. This is going to be based on the angle. Now, since we have low dispersion, it's going to be more or less correlated with low values. High values are the opposite. So here's the idea. Under feeding, we're going to have a low value, which means that the angle of swimming at each step is going to be uncorrelated to the previous one. So if you're going a direction, you could just equally go in any other direction. At high values, it's going to be much higher. Okay, so that is, let's just show you an example of this just a second. So we're going to introduce to you something called a okay. We're going to introduce something to you called a von Mises distribution. What is that? Let's look at the function RVM. Random generation from the von Mises distribution, or von Mises. So this creates random numbers from the von Mises distribution. The von Mises distribution is a circular distribution. So it goes from 0 to 360. And let's just do an example here. So let's do a histogram of RVM. So this was really similar to R norm that we used earlier in the class. Histogram of RVM, that's right. Let's pick 1,000 variates with a mean of 180 and a dispersion, this is the concentration or dispersion parameter, of 0.1. So let's run that. So this is going to be 0 to 2 pi. So this is 6.28, and it looks pretty flat. So even if we put in 0.01, 1,000 numbers there, it looks like always giving us a pretty flat distribution. But if we put in a high one, I guess the mean here shouldn't be in degrees. It should be in radians in this case. So that would just be all right. We'll change that to degrees in a minute. Now let's put on a high dispersion. And you can see that all of the values, the random values, are clustered around 3.14. So if an animal is picking this angle of 3.14, so for 1 pi, it's going to keep heading in that direction with a random variate with that dispersion parameter. And you'll see how this works out in a bit. Okay, so the other thing we have to do besides the dispersion parameters are step lengths. So let's make feeding the mean of the distance equals 5,000. So it's going to be the average step, and the searching mean distance is going to equal 50,000. This is in meters. So it means if you're feeding, you're taking shorter steps. If you're searching, you're taking bigger steps. Let's go ahead and create a simulation of a single animal. So let's start with a position, a random starting place. Starting position is going to, what we're going to do is we're just going to sample the lawn and lat. So if we look at the lawn, we subset it down to those values and the latitude. We can also use the sample function, lawn, and just ask for one value. And it's going to give me one random value from lawn. I can run it again, give me another random value, and so on and so forth. So we're going to create a matrix. Okay, so what is this doing? We're concatenating a random sample of our longitude and our latitude together, and we're sticking that into a matrix with one row and two columns. So if I run pause, that's going to be our starting point. If I run it again, that's our new starting point. So it's a random generator, so that's going to be our starting one. We're also going to pick a random bearing. We're going to pick RUNIF, or random uniform. I'm going to pick one number from a random uniform distribution. Then that distribution is a min equals 0 and a max equals 360. So this is going to be initial random bearing for the animal. So which direction is it going to swim first? Okay, this is picking the initial random position. Okay, all right, sounds good. So these objects below will keep track of the chlorophyll that we encounter, distance, and bearing for the track. So this is going to be fill track equals null, dist right. I feel like we're missing one thing here. Oh yeah, I see what we need to do. So let's come back up here to our chlorophyll mat. Let's just go back and look at our picture here of chlorophyll. Now, it's possible for the animal to swim off the screen. So of our little area. So what we're going to do is we're going to put a fence around it. And the way that we're going to do that is we're just going to take chlorophyll mat This is going to act like our electric fence, a pen. So if our simulated shark hits it, it just dies. And that's just the way it is in this simulation. So chlorophyll mat, the first row, all columns, is going to be NA. And we also want to do that for the first column, all rows, is going to be NA. And then we're going to say chlorophyll mat, looking at the number of row of chlorophyll, so the max one, so this is going to be number of rows chlorophyll mat is 248, so the 248th row is going to have an NA, and we also want to do the same thing for column. We want to put that in the column argument. Yeah, so if we now do an image.plot, you'll see that we now have we have NAs here on the edges. It should be there. I believe so. Just make sure. Maybe just one of them worked. There it is. And you can see the little little fence there for us. Okay, let's get back down to the simulation. So we are going to create a random initial position, random bearing, keep track of the track properties. And so now what we're going to do is simulate a single animal track. And I'll just put note animal hits and NA in the CHL field, it dies. Sad face. But that's okay. So let's do 4x in 1, 2, 3, 65 days. This is going to be our simulation. We need to figure out, first, get an index for which grid cell is closest to the animal. So we've got it in there, but we have to figure out which index, which row, which lon lat index that is actually closest to. So we're going to make a function called lon ind. And we use a function called which.min. Which.min is asks what's the minimum of any function. So we want to do the absolute value of the position x. So remember what pos is that. Minus ln. So if we subtract these, let's just say x equals 1. And let's just plot this. So you'll see that, you know, it doesn't look like there's any, it looks like the minimum's down here, but we want to actually know which one's closest to 0. So that's what we're going to take the absolute value of it. Which one is closest in distance? So let's plot the absolute value of that. Okay, so this term, you can see that is the closest term. So if we do which end, 30, the 30th one. So the 30th longitude is our closest one. Lat end is going to be the same thing. Except this is going to be the second row. So our position, we want to look at this one here. So what's our lat end? The 61st. So that means that row, in our chlorophyll matrix, row 30, column 61 is the closest chlorophyll value. And we're going to take that chlorophyll value and extract it. So our chlorophyll value is going to be CHL nat. And it's going to be our lon end and lat end. So the chlorophyll value for this, oops. Okay, so the CHL value is 0.47. So that's the value of chlorophyll at the starting position of the shark. I'm going to now append that. Okay, so we can keep track of that. All right, so the next thing we're going to do is put in here what's called a conditional statement. If the CHL value is NA, then the animal stops its path. If it is a value, then it executes the codes between those little signs. Okay, here we go. Put an if statement. If it's not an NA, so is this case, so chlorophyll value we said was that. Is this an NA? That's false, but the exclamation point in front, we want to ask the opposite. Is it not an NA? That's true, it's not an NA, it's a real value. Now we're going to do something between these brackets. And if. What are we going to do? Hey, here is the next conditional statement. If the CHL value is greater than CHL thresh, then it is in a feeding behavior. It will have a feeding dispersion and a feeding step length. If not, then it will have a searching dispersion and searching step length. All right, how are we going to do that? Okay, so we already have one conditional statement that we need to add. We're going to add another one here. So now we're going to say if the chlorophyll value is greater than or equal to the chlorophyll thresh. Okay, so if it's greater than chlorophyll threshold, now we want it to be in the feeding behavior. That means that our dispersion equals our feeding dispersion, and our mean of distance equals our feeding distance. Close that, and I'm going to put else, right? So if this is not true, if it's less than it, then our dispersion is going to equal our searching dispersion, and our mean of distance is going to equal our searching. Right. Okay. So this is contained in here. So this is and if of chlorophyll thresh. So it's going to come in here and say, is it not an if it's not an NA, then go to this conditional statement, which is test to see which condition we need to be in. Okay. All right. Now it's gonna jump out of this statement, and once we have our feeding dispersions, now what we're gonna do is calculate our bearing. So our bearing is going to be a random von Mises. I'm going to pick one number, one random number. Remember, we already have a random bearing. Oh, do we not? I should have run that. Let me come up here to the top. Make sure I have everything I need for this loop. X equals 1. I'm going to jump in here and run these two things. Okay. Now, we already know that it's a value, so the CHL value is, okay, it's a value, that's good. If this, so what do we end up with here? Oh, searching mean of dist. This is supposed to be mean dist. There we go. Try running this again. Okay, so that means our disp value now is our searching dispersion, and our mean of distance is 50,000. So that's what we set up here. So the conditional statement came in, it said chlorophyll value greater than the chlorophyll threshold. It's not in this case. So we're going to do this else statement. Now we're going to come in and pick the new bearing. So RVM, we're going to pick one random number. Okay, say the mean of this distribution is going to be pi divided by 180 times the bearing. Okay, so remember the bearing, the random bearing that we're starting is with 10 degrees, but of course we need to change this into radians, and that's how we do this here. Right? It's going to be that. We need a dispersion, and our dispersion. Now we're going to take this random number, this number, and we're going to convert it. Well, so this is going to generate something in radians, and we're going to want to, well, we'll keep generating random numbers with the mean of this thing, and we want to convert this back to degrees. Pi. So bearing now is 41. So now we're going to store that bearing in our bearing track. So we can look at it later. Okay, so we've got a dispersion, a mean of the distance. So we've got our dispersion, so we've got our new bearing, and now we need to choose the distance. So we want to choose the distance to be absolute value. I'm sorry, let's just do this first. R norm, done this before, one number, mean of distance, and we'll just plug in a standard deviation equals 1,000. Just in case it returns a negative distance, we're just going to stick an absolute value in front of this. That shouldn't happen very often. So distance is now, that's how far we're swimming. And we're going to store this. Choosing distance. Right? And we want to same thing we did here. Store our distance. Okay, now we have a direction and a distance that we want to head. So we need to now compute the next ln and lat based on the bearing and distance. How are we going to do that? We're going to call this the end position of our one step length here. We're going to use a function called dest point. So do question mark dest point. Destination giving bearing and distance. So given a start point, initial bearing, a direction and distance, the function computes the destination point traveling on the shortest path on an ellipsoid or on the great circle. So P is the longitude and latitude of points in degrees, can be a vector of two numbers or a matrix. B is a bearing, D is a distance in meters. There we go, that's all we really need. Destination point, so is now the xth term in position, which is just going to be, remember, our starting point, that's where it's starting, and then bearing and distance. Those are defined. So end position, oh, better spell dest point right. End position. That's our new position, ln and lat. Okay, so what are we going to do now? Now we're going to take our position and we're going to row bind our initial position with our new position, end position. And now print x. So that's what's going to happen. Now we also need to put an else in here. Remember, this is left over from this if statement, if it's NA. So if it is NA, now else. So if it's not an NA, do all this stuff we did in here. If it's not an NA, or if it is an NA, else our pos equals, I put this same command in here, our dist track equals C dist track A, and our bearing track equals bearing track NA. Now this is going to be and if for testing for NAs. And oh, we already had that end if in there. And we also have our end x. Okay. So let's take a look to see what is actually going to happen. So let's come back up here, clear these out for 1 and 365. Okay, and 1 to 365. And now let's do a image of the chlorophyll field. Image.plot, long, flat, that, equals true. Go ahead and stretch that out. Now, what we're going to do is we're going to add the points for the track for 1 year. So what do we have? Well, we have pause. We have all those points for 1 whole year. Okay, so this is going to be points. Type equals O. There's our track. Bet it did. Kind of swam around there randomly. And let's take a look. Let's put the endpoint. Let's color the endpoint red. Just want to put the end one in there, which is going to be in row pause. So that's the end pause value. So I'm looking number of rows, total number of rows, first column, and total number of rows, second column. Let's make it red. That's where it ended up. So started over here, ended over there. Okay. You actually have to come all the way up here to where we define the initial random position. So come back up here to 40, copy down to our little line 106 there. If you run it, there's an animal that died in the fence down there. Try running it again. Here's one that also died in the fence. Here's another one. Looks like it searched for a while, then changed its behavior for a while. Another one that found a big hunk of chlorophyll and stayed there. Another one that died in the fence. You can see how many times you die based on the feeding parameters that we have here. So these are all simulations of quote tracks as they're switching from feeding to dispersion type of behavior. Okay. So you can mess with the dispersion parameter a little bit, either dispersion parameters or the threshold. In fact, I can just come up here and mess with the threshold. So if we want it to be in a constant feeding behavior, I would just shrink this to 0.5. 0.05, and then come back up here to, we'll copy from here then to the bottom, and you can pretty much make the shark stay in the same place. Oh, no, actually, it stayed in, it was lower than 0.05 there. Okay, all right. So, or I can always have it searching if I have my chlorophyll value high enough. So I'll let you guys mess with that. All right. So what happens now if we want to simulate a whole bunch of animals? A whole bunch of animals. Well, actually before that, let's do a little sleuthing here. In fact, I'm going to come back. I'm going to run this on. Okay, that looks like an interesting one. All right. Okay, so make sure your simulation goes to 365, right? So no sharks died in the NA fence. So here we go, we got a nice one. Looks like it come up and did some things. Let's do this. Let's go ahead and make a layout. We've done this before. Matrix of 1 to 3, and I want 3 rows, 1 column. And I'm going to plot 1, 2, 3, 6, 5, the bearing track. So what did the bearings do? And then I'm also going to plot the distance track, and I'm going to, same thing here, plot the chlorophyll track. Okay, let's do this. All right, so here's the bearing track. You can see it was pretty constant for a while. Here's chlorophyll, right? Remember our threshold was at 0.15, so it looks like it got up into the threshold where now we're taking really short step lengths and really random bearings. But down here at really low chlorophyll values, our distances are much larger than these, and they're much more constant in general, much more constant. So you can see that switch in the behavior. Okay, what if we want to simulate not just one animal, but 100 animals? So we're going to change this up just a little bit. 100 animals, or sharks in this case, one at a time. So this loop as above, right? So I'm just going to grab these things up here. Chlorophyll threshold, feeding dispersions. These things in here, you already know what they are. We'll paste them down here. All right. And the only thing that really changes is the way we do the start position. So start position for these animals is now we're going to sample ln 100 times. Oh, ln, not ln. For 100 starts, replace equals true. So when we sample, you know, if we sample one, we want to throw it back in the mix to see if we can sample it again. This one concatenates these together. C-bind them. So these are the start positions for all of our 100 animals. We're just going to loop through each one. That's where they're all starting. So randomly starting places in our field. And we're not going to trace out each track, but we're just going to keep track of each end position. So for z in 1, 2, n row, start, pause, okay, do this. Then we're going to have an nz down here. So in this case, our position matrix of start, pause, the zth animal, and our initial bearing, $60, and the next part is going to be 365 days for each animal. And we're literally going to grab just our loop from up here and get down here to end x, stick that right in here. And here it is. The only thing we don't need to do is keep track of our, I guess we could. Fill track. I don't think we need to keep track of it in this case. So our conditional statement. And then in here, right after our end x, our track our end position. And we're going to take the last position for each row. Right. That should work, but we'll see if there's any bugs here. Oops. Oh, we'll go ahead and save this file. All right, let's give this a whirl. Well, seems to have worked. It's looping over those 100 animals. Okay. Now, let's do a plot showing the starting points. Two rows, one column. Okay. Points. color to be white, and the point character 20. So this is where the animal started. Right? Randomly all over the place. Okay. And now let's make a plot showing where the animals ended after 1 year. I'm going to take this again. And be red. And this is going to be the track end position. That's where they ended. Right? See, a lot of them died here on the edge, some of them ended up in here. And what we want to do now is maybe put some arrows on there. I'm going to add arrows. Actually, we'll put it in here. So the arrows command are just going to connect where these guys started to where these guys ended. So arrows, you look for the coordinates to draw. You need an X initial, a Y initial, so that's where your starting point of the arrow is. Then your X1 and Y1 is where it ends. So let's go back over here. Our arrows, our X naught, is going to be the start position, first column. It's our longitude. Our Y naught is going to equal the start position, latitude. X1 is going to equal the track end position, first column. X2, Y2, Y1, Y1 is going to equal this thing, second column. Make them white arrows. And align weight 2. Oh, this needs to go away. Yeah, okay, so let's run these together. All right, so here's where the animal started. This is where it ended up. It's a little busy, but you can see where a lot of them ended, but you can probably adjust the feeding and dispersion parameters to make these things change. And that's going to be all part of the homework, to go in here and manipulate these values to make your sharks do different behaviors, both singly and with the 100 animals. So